ambiguities are inevitable in human-robot interaction, especially when a robot follows user instructions in a large, shared space. For instance, on the left, the user is likely to expect a clean cup from the shelf, whereas on the right, they might expect a dirty cup from the table while doing the dishes. In such cases, users themselves may be uncertain about the object's location, for example, where they left the cup after having coffee. To handle these situations, additional semantic information about the queried object, such as whether it is clean or empty, can provide valuable hints for the robot to reduce its search space. Previous studies on object search either relied on one-shot inferences without incorporating effective clarification strategies, or focused on fixed visual scenes, assuming the queried objects are in the robot's current viewpoint, and suggested model-specific approaches. To address these limitations, we leverage informative follow-up questions and propose a model-agnostic method that enables robots to find the locations of objects in household settings. We first build semantic encoders, or use LLMs, to obtain the relationships between object semantic properties and their location and room features. Then, using these representations, we present an informative clarification technique that maximizes the system's information gain in case of ambiguities. Finally, we propose an iterative prediction process that first identifies the likely room containing the object, then, conditioned on the room, the object's likely placement, as in the following example.
Hey there.
Hey, I'm looking for my yellow water bottle.
Let me help you. How is the bottle's fullness?
It's empty.
I see. How is the bottle's cleanliness?
It's dirty.
It can be in the kitchen, on the countertop.
Prior to evaluating our method, we conducted a pre-study to assess the human instructions, specifically for object room and location features in ambiguous setups. We observed that users provided these features correctly in only 36% of instructions, supporting our motivation to design an informative clarification approach eliciting additional information. Finally, in our evaluations, people watched video clips of homes from the 3D Matterport dataset and described selected objects. Using these descriptions, we compared the performance of varying embedding models and LLMs. The results show that, regardless of the model, our method improves performance and enables the robot to make correct room and location predictions on its first attempt.